Hey students, welcome to lecture number 10 of Linear Algebra 2. So today we want to talk about some applications of eigenvalues and eigenvectors. So what we want to do today is we want to do four things. So first I want to talk about how to calculate eigenvectors and eigenvalues numerically, and then I want to talk about three applications. So here in the first part, so we learned that to calculate an eigenvalue of a matrix or linear map means that we need to calculate the characteristic polynomial and then find all zeros of this polynomial. But in real life application, the matrices you're dealing with are usually not 2 by 2 or 3 by 3 matrices, but they can be 100 by 100 matrices, and in this case you would need to find a zero of a polynomial of degree 100, which is not easy to do. But this is also not what you basically want to do, because there are really easy algorithms to give you at least numerically a good approximation for eigenvalues, or at least for one eigenvalue, and also for an eigenvector. And this I want to talk about first, and then I will also try to explain how to do this in Python, and then I will give these three examples. So the algorithm we want to talk about is so-called the power iteration, or it's also named after this guy von Mises. It's also called von Mises iteration. So the basic idea is that whenever you have a matrix A and some random starting vector, which should satisfy certain conditions, then what you can do is you can multiply this matrix several times to this vector V, and then this will give a vector V. And then the statement is that this vector, after multiplying this matrix A several times, that this will actually be a good approximation for an eigenvector of this matrix A for its so-called dominant eigenvalue. And this means that this eigenvalue is the largest of the eigenvalues of A. And this I first want to make precise. So, we know examples that there can be matrices without any eigenvalue. So in this case, this algorithm would fail. But for example, so let's make this more precise. Oops. So let's now consider an n by n matrix, which is diagonalizable, meaning we can find a basis made out of eigenvectors, and then we can bring this A into a diagonal form where the eigenvalues are on the diagonal. And let's assume we have eigenvalues. So let's call them lambda 1 up to lambda n. And of course, so this is now in n dimensions. So we can have up to n eigenvalues, but it could also be that we have well, in this case we have n because it's diagonalizable, but some of them can also be the same. For example, the identity matrix just has eigenvalue 1. And now we assume that lambda 1 equals lambda 2 up to lambda d. So the first d eigenvalues are the same. And then this eigenvalue lambda 1 is larger than the others. And this is what we mean by dominant eigenvalue. So we want that the absolute value of this number is strictly larger than the other eigenvalues, where this j runs from d plus 1 up to n. So this just means we have some matrix A which has these eigenvalues, and then we order them in such a way that the first d eigenvalues, which are the same, are the ones with the largest absolute value. And now consider a basis of eigenvalues, of eigenvectors. Sorry. So let's see. We can say eigenbasis. And here I mean that B1 is an eigenvector with eigenvalue lambda 1, and so on. So now let's see what happens to a matrix A if we do this to some vector V. So first of all, because this is a basis, we can write any vector V as some linear combination of these basis vectors. So j goes from 1 to n. And these alphas, they are just real numbers. And now we assume, so this is one of the conditions here on this so-called random vector, that the first d parts here, that this is not the zero vector. So in other words, so here the first d eigenvalues are the same, and therefore the first d eigenvectors are a basis for the eigenspace of this eigenvalue. And this condition here means that if I write an arbitrary vector in this basis, then the part in this eigenspace of this first eigenvalue is not zero. But for the application, you usually don't need to worry about this because due to numerically, if you do it numerically, it's not precise anyway, and therefore you don't really have a zero. But now for the calculation we want to do, we want to see what happens now if I multiply this a, the k's power of this a to the v. So this is by definition. Well, we write this v in terms of our eigenbasis. And, well, now I can multiply this ak to the bj. And because this bj is an eigenvalue with eigenvalue lambda j, so here maybe, so if I multiply this, then this is lambda j bj. And if I do it k times, then I get k times this factor lambda j. Therefore this sum here is j goes from 1 to n, still this alpha j, and now I have lambda j to the power k bj. Okay, now what we want to do is we factor out lambda 1, so we want to write in front, rewrite a lambda 1 to the power k. And here lambda 1 up to lambda d is the same. So the first d parts here, when j runs from 1 to d, I always have this lambda 1 to the power k. Therefore the first sum here is just alpha 1 b1 up to alpha d bd plus, and now I have the rest where this j runs from d plus 1 to n. And because I factor out this lambda 1, I have lambda j divided by lambda 1 to the power k alpha j bj. Okay, and now, so one of this condition was that this lambda 1 is strictly larger than this lambda j. So therefore, if we look at this term here, the absolute value of this number is smaller than 1 because this lambda j is smaller than lambda 1, and therefore this number is smaller than 1. And then therefore you learn in calculus that this term here, if you send k to infinity, then these numbers get smaller and smaller, and therefore this goes to 0. And so if you consider large k's, so well, we will not send k to infinity, but we consider k to be really large, and therefore this part here gets really small, and this part here, so this is now the main part, and this, because all these b1 up to bd are eigenvectors for eigenvalue lambda 1, so this here is an eigenvector for lambda 1. So we see that if we look at this product here, and we have a large k, then this contribution here of these eigenvectors for other eigenvalues, say, they get quite small, and the main contribution is this part here. So, therefore, this suggests the following algorithm, so the power iteration algorithm So one problem here is, of course, when we send k to infinity and this lambda 1 is greater than 1, then this also gets quite large. So instead of multiplying with the power a to the k, we multiply one time with a, get a new vector, and then normalize this vector, and then again multiply with a, normalize this vector, and so on. So the algorithm is that we start with some vector v0 and say this is some, so this v is some random vector, where by random we shouldn't choose the 0 vector because then everything is 0, but usually just taking some arbitrary vector works. And then we define the first, so vk plus 1, so by multiplying this vector v0, or the vector vk, so we start with v0, so in the case k equals 0, v1 is a multiplied with v0, and then we normalize it, meaning we divide by the norm. And then we do it again and again, and in the end we will see that vk goes to converges to an eigenvector of a for its dominant eigenvalue, lambda 1. And this dominant eigenvector just means that this condition here is satisfied, that this is the largest of these eigenvalues. Okay, so let's do this in Python. Okay, so this here is a so-called Jupyter notebook, and maybe some of you know Python, but I will also put a link to this notebook into the Facebook group of the lecture. And so if you work with Python and you want to do some math, you need to import this NumPy, which includes all math operations you want to do, and also it has a big linear algebra package inside. And so, for example, a matrix in Python is written as an NP array. So this here is a 2 by 2 matrix. So this is the first row, and this is the second row. And then vector is also an array, but now it's, well, in this case it's a row vector, but you shouldn't need to worry about this too much. And then what I do here, so what you do for multiplying a matrix with vectors, just this function np dot. So in this example here, we have the matrix A is 1, 2, 3, 4. The vector V is minus 1, 2. And then, of course, A times V should be, so minus 1 times 1, and plus 2 times 2 is 3. And then 2 times 4 is 8, minus 3 is 5. And this is just what you see here. And now, to implement this power iteration, one can define this following function here. So as an input, we get a matrix A and some k, which will be the number of steps. And then here, this is the command to get some random vector. And this just gets the size of A. So this in our example was the n. So this gives a vector of size n with random entries. And then what this does here is just do k times the following thing. So this is what we called a vk. So we take the product of A with the current vector v. Then we calculate the norm of what we just did, so by this command here. And then we divide this vector by this norm, and this will be the new vector. And then he will use this vector here again in the next step, and this he will do k times. And in the end, he will return this vector v. So, for example, we can do, let's also take this matrix here, 1, 2, 3, 4. And then we can do this power iteration maybe 3 times. and print out the vector and so the output of this function here. So in this case, so if we do this, we get, so this is just the matrix A, and this is now the output. So the statement there is that that we get V is, well, it's a different V, that this is about 0.41 and 0.909. And we see that in the next part what we do, we multiply A with this vector V to see what happens, and it's 2.23 divided by 4.88. And why is this now an eigenvector of this matrix? Well, we need to check if this vector here is just a multiple of this vector. And this, for example, we could do by see what is this vector here, the first entry, and we divide it by the first entry of this here. So it's 5.3. Well, actually in this case it's the second entry, because the first entry is when we take the 0 part. And here we see that in both cases, so the first entry is 5.3 times, so what this says here now is that this is 5.3 times this vector V, because we checked that this divided by this is 5.3 and this divided by this is also roughly 5.3. Okay, so to get the eigenvalue out of the eigenvector, which comes out of this power iteration, you can divide out, you multiply the matrix A with a vector and divide out the first entry here by the first entry of the vector V. So for example, you could define this function, give the eigenvalue by doing this power iteration, and then the lambda is just you take the first entry of the product and divide it by the first entry of the vector and then return this eigenvalue. So in this example here, what this does, give eigenvalue of my matrix A after doing 3 iterations. Oops. So in this case he gives 5.3. And we also see that if we just do it once, after one step is 5.56, and if we do it 10 times, it's 5.372. So it doesn't really change after. So already we see after 1, 2, or 3 steps, we are quite close to the actual number we want here. But also the speed of how many k's you need depends on how fast this factor here goes to 0. Meaning, if let's say the second largest eigenvalue is quite close to the largest eigenvalue, then we will see that this is just a little bit smaller than 1, and therefore this goes quite slowly to 0, and therefore then you need to get larger k. So if you play around with this and you will compare 2 different examples where you have one matrix where the dominant eigenvector is much bigger than the other eigenvectors, the eigenvalues, then you will see that this algorithm is quite fast. So after 1, 2, 3 steps, you will already get a good approximation. But if you have another example where the dominant eigenvalue is quite close to the second largest eigenvalue, then you will see that this algorithm takes a lot of time, and you need to take k equals 100 or something like this. Okay, so now we know how to actually calculate eigenvalues and eigenvectors. At least we know if we have a matrix, we have an algorithm to get the largest eigenvalue and also one eigenvector for this eigenvalue. And this we now want to use in some application. So the first application we want to talk about is similar to our bunny example, where we talked about the population of some bunnies. But maybe this example is not so interesting. Maybe a more interesting example is to consider the population of a country. For example, this is the population of Japan in the year 2017. And what this graph tells us is So here we have different age groups. So each of these age groups is 15 years. And for each of these age groups, we see how many people in Japan are in this age group. So we see that in this year, 2017, 12% were younger than 15, 14.6 were between 15 and 29, and so on. So the maximum here is, we have a lot of old people here, between 60 and 74. So this information gives us some vector. So we could say the vector of the population in the year 2017 is, well, I have 12.4. So either I could write down now the percentages or the number of people in millions. But now I just write down these numbers. But you could also think maybe this means 12.4 million people. So we have a vector like this. And now we want to understand what happens in 50 years or 100 years with this population. And of course we need some further input. So we need to know how these age groups interact with each other. So for example, we need to know from these people in this age group here, younger than 15, after 15 years, how many of them will survive. So we need to have some survival rate. And we also need to know for each of these age groups how many of them create new people. So we need to have some fertility rate for each of these age groups. We need to have some factor, how active they are in bed. So this we will now. So we have a fertility rate, meaning how much birth is given for each group. So in this case we have 1, 2, 3, 4, 5, 6, 7 groups. So this fertility rate is for 1 to 7. And what this means is really, so F1 somehow gives a factor that after one generation, so one generation in our case here means 15 years, how many of this group will again be in this group. So this F1 will be a factor between 0 and 1. And also F2 will give a factor how many of this age group will, after 15 years, make new people here. And also F3 and so on. And then we also have the survival rate. So this we also have from 1 to 7. But we usually assume that the survival rate of the last part is 0. But what this means is a factor how many of these under 15-year-olds will be in this age group after 15 years. And here S2 will describe how many of these people will survive and will be in this age group, and so on. And therefore we can make some equation including this vector here, what happens after 15 years, and this we will describe by multiplying with a certain matrix which includes these numbers here. So let's see. So I want to find a matrix which describes what happens after 15 years. So here now I have the vector with the entries from 2017. And what do I put in here? So this entry is new age group for the younger than 15 years old. So in this number, how can we construct this number out of these numbers? Well, it depends just on these fertility rates. And we see that, for example, the number of people coming from this group here, so how many under 15 years old will also create a newborn. So maybe this number might be quite small in reality, but here we have the factor f1. And then from this part, we will see this factor here means how many of these people here will contribute to this factor here. And this is exactly the fertility rate f2. And then we have f3, f4, f6, and f7. And this will give the new under 15-year-old in the after 15 years. And now the survival rates. So, for example, the age group 15 to 29-year-olds. So the only input for this age group is, of course, this age group, because this age group, they will not get younger. So we just know that the new 15 to 29-year-old is S1 times this one here. And this means that this factor needs to multiply it with S1 here. So we have the survival rate S1 here. But the rest is 0, because nobody can give something there. But then we also see that the third age group will be the second age group multiplied with S2. So this will be a 0. And then we have S2 here. And then here we will have F3, F4, S6. And here in the last age group, so here we would have S6. And maybe in reality it also makes sense to say, well, maybe some of these also survive, but usually this is set to be 0. But this is S7 here. But maybe I will leave it out here. So, and the rest is just 0. So we see here on the diagonal we have zeros and just one number here. And in the first column we have these fertility rates. And these numbers under the diagonal are given by the survival rates. And multiplying with this matrix, this vector, will give us the vector. So this will be the vector for the year 2032, because one generation is 15 years. So 15 years after this will be this year here. And then we could apply again this matrix. So this is now a matrix A. We could apply it again to this, assuming that these rates do not change. And then we might ask, what happens to this population here? And now the question is, what do eigenvalues and eigenvectors of this matrix tell us for this real-life application here? So first of all, this type of matrix is called a Leslie matrix. So you can look this up and see more examples where this can be applied. So you always have some shape like this. And so the interpretation now, is that, so what is the eigenvector? So what would be an eigenvector in this scenario? This would mean that I have some distribution of the population, and after 15 years I have the same distribution of the population, but maybe multiplied by some factor. But still, assuming that, for example, if this would be an eigenvector of this matrix here, then this would mean that also in 100 years I still have this shape of the population. Maybe the population grows or shrinks, but still the main people will be old people. But if this is not an eigenvector, and I multiply with this matrix, then maybe the shape of this graph changes, and maybe after 20 years I will have a lot of young people, because maybe the fertility rate is quite high. Well, in reality it's quite low, but assuming the fertility rate is quite high, then maybe we get something like this, and maybe this would give an eigenvector, and then this would mean that after 200 years we will always have this shape, assuming that these rates do not change. So the eigenvector is somehow a stable population. I hope it's clear what I mean by this. And what is the eigenvalue in this example? So the eigenvalue just describes the growth. And here I should say the dominant. the dominant eigenvalue, because applying this matrix again and again, if we go back to our calculation here, applying matrix again and again will lead to this part here, that the dominant eigenvalue is the main part which plays a role. So in this population example, also the dominant eigenvalue explains, so this gives the growth rate of the population. So even if the starting vector here is not an eigenvector, the dominant eigenvalue of this matrix will still describe, in general, if the population will get bigger or smaller. So so let's call this lambda. So then it's important. So the question is if this lambda is smaller than 1, lambda is 1, or lambda is greater than 1. And each of these, so if it's smaller than 1, then the population shrinks. If it's equal to or near to 1, then the population stays the same. And if lambda is greater than 1, then we get more people here. Okay, so this is now one real example, but now let's do one more mathematical example where we actually calculate something by using a Leslie matrix like this, but for a smaller n. So we want to consider this matrix here, a colorful matrix. So it's a 3 by 3 matrix, and it's a Leslie matrix. So in this case we have 3 H groups, and we see here that this number here is the fertility rate from the second H group. So this 0 here means that the H group 1, that they do not produce any babies. So the only contribution to the new A1 is the H group 2 and the H group 3. And we see here that this 4/5, so this is the survival rate of A1. So maybe this we could write down. So this means 4/5. So this means 80% survival rate for A1. And this 2/5 here means well, it's 40% survival rate for the H group 2. Okay, so now let's calculate, in this case, what is an eigenvector and eigenvalue. So, and now we do the classical case. We just consider the characteristic polynomial. So f a lambda in this case, so it's a determinant of minus lambda 3 to 4/5 minus lambda 0, 0, 2/5 minus lambda. And then, well, this I give you for free now. You can check that this is this polynomial here. So we are interested in the eigenvalues of this matrix. So first, so in this case the eigenvalues are not really nice, but let's plot this function here. So we get, if you plot this polynomial here, you get this graph here, and you see we have actually 3 zeros, so we have 3 eigenvalues, and the dominant eigenvalue is now the one which is most on the right. So here this is lambda 1. So in our case the eigenvalues are, lambda 1 is around 1.668, lambda 2 is minus 1.39, lambda 3 is minus 0.27, something like this. So we see here the dominant eigenvector is 1.668. So this means now the interpretation that for population behavior like this, the population will increase, and each generation it will roughly increase by 66%. So so population growth is roughly 66.8%. So you could check that if you multiply this with some starting vector, 1, 2, 3, and then multiply A several times, that in each step the number of age group here is roughly increased by 66%. And what is an eigenvector for this eigenvalue? So this is roughly given by 8, 9, 4, 3, 10. So you can check that if you would subtract this lambda from the diagonal and calculate the kernel, then one element in the kernel is roughly given by this. Here I left out some decimal places. But what this means is that if you would start with a population like this, so we have a lot of young people here, and then in this age group we have 43, in this age group we have 10, then after several generations we will still have a lot of roughly twice as much in age group 1 than in age group 2, and roughly 9 times than in age group 3. And this will not change because this is an eigenvector of this population. But if you would start with some other vector, then, for example, if you start with a lot of old people in age group 3 and apply this, then this will slowly shift to this part here. So after a few generations you will have a lot of young people. Okay. And maybe this doesn't describe people, maybe it describes some beetles or something like this. Or maybe again some bunnies. Okay, so this was the one example. And this example is also included in the Jupyter notebook, where you can check these numbers with Python. And what I want to do now is talk about so-called Google PageRank. So oops. I hope this is visible. So what is the main idea? I mean, every one of you should be familiar with Google, and the Google is a search engine. So if you search for something, you get search results, and of course, if you, for example, search for the word Nagoya, then there are a lot of pages which have this word Nagoya on them. But Google somehow needs to decide which site they should put on top. And so they need to give an importance to each of the websites. And how they did it at the beginning, and now it's a little bit more complicated than this, but what they did just at the beginning is the so-called PageRank, where page here stands for the last name of Larry Page, so it doesn't stand for web page. And what this algorithm does is it gives importance to websites depending on the connections between these websites. Meaning, so we assume here we have a small subset of the internet. So for example here we have the homepage of Nagoya University, the homepage of the Japanese government, and the math department homepage. And then this homepage here, and also other homepages. And then I draw a line or an arrow here between two pages if there's a link on this page to the other. So for example, there's maybe a link on the page of the Japanese government to Nagoya University, and also on the homepage of the math department there's a link to Nagoya University, and I also have a link to the math department, and I'm listed there as a faculty, so there's also a link to my page. And now we want to decide on these links which of these pages is the most important ones. So if I search for Nagoya now, then each of these pages has the word Nagoya inside, but I should maybe put the Japanese government on top of this list. But this we want to see just depending on these links. So now one approach would be to say, well, the page where most people link to is maybe the most important page. So, so for example, here we see that there are 1, 2, 3, 4 links are going to there. And so, for example, for this to this page, there's just one link. So it would be easy to just count how many links are there to one page and then say I just order them by the number of links. But of course, this has a problem because if the algorithm would just count the number of links, then I could give you the homework to create your personal websites and then force you to put a link on your website to my homepage. And then by this, it's easy for me to increase the number of links to my homepage. But of course, this shouldn't count so much because these new created websites, they are not really important themselves. So we shouldn't just count the number of links, but we should also count where are these links coming from. So if this page here gets a link, let's say from Nagoya University, then this is then this should count more than a link maybe from the math department or maybe from my homepage. And therefore, the importance we want to assign to these numbers will depend on the number of links, but the links will also be weighted by the importance itself. And we will see that this then leads to an eigenvalue problem. So, first, so we have these 6 pages, and now we want to define a vector x1, x2, x4, x6, and now these numbers x1 up to x6 should give a number of importance for these 6 websites. And if this number is higher, then this website is more important. And the thing I described, meaning that we want to count the number of links, but weight it with the importance, this leads to the following equation. So first of all, we have a big matrix here, which somehow describes where these links go. So here we have web page 1, which is this page here, and in this row here, I should see from where does this page get a link. So first of all, I don't count myself, so I don't give a link to my page itself. But now I can ask, is there a link from the page number 2? And in this case, there I actually have a link. But what you also want to do is that if a web page sends links to a lot of places, then this web page just has a certain amount of power. So if it sends to a lot of places, then these links are also a little bit weaker. So meaning that these 3 links here, by this web page here, should just have a factor of 1/3. So therefore, this one link that the math department sends to my site here, so this factor here is just 1/3. And since there's no other link to this page from other places, I will write just zeros here. And this, so if I multiply with this, so I see that in my case, this home page here, the importance is just 1/3 of the importance of the math department site. So this is what I want, and therefore what I want is that this actually equals exactly the importance of these sites. But maybe let's do more example here. So for example, for the second site, so how many links are going into the second page? Well, we have 1 from my page, and I just have 1. So my full power somehow goes to this page. And then there's 1 link coming from page number 3. And page number 3 sends out 1, 2, so 2 links. So from page number 3, this page number 2 gets 1/2 of its importance. So we get this here. And there are no other links going to this site here. And now let's write the rest so you can check that then. So first of all, if you look at the columns, so this column describes the links going out from this page here. And this somehow describes the links going in to this page. So in this case, I just have one here, just one link going to page number 2, and therefore the full power goes to this. But page number 2 has 3 links going to page number 1, page number 3, and page number 4. So here in this column we have 1/3, 0, 1/3, 1/3, and 0, 0. And this you can write down for the rest. So if you compare this matrix, zero, 1/2, 1/2. So most of the sites have exactly 2 links going out. And this is now the equation we want to solve. So this is exactly the statement that the importance of a page, for example here, the importance of the page should depend on the links going to this page, but I should not just count the number of links, I should factor this with the corresponding importance of these sites which link to this page. And therefore we get this equation that this vector with this should give the importance of x3. And we see here we have the equation that the matrix x, A times the vector x, should be the vector x. Therefore, the solution to this problem is to find an eigenvector to an eigenvalue 1. And in this example here, you can, so maybe now this I can delete. So want to find eigenvector with eigenvalue 1. And in this case, we are somehow lucky because this matrix actually has an eigenvalue 1. And so in this example, let me check. In this case, we get that if we can 0.8, 2.5, 3.3, 4, 2, 1. So with this vector you can check that A times x is actually x. So what do we see here? So we see that page number 4 has the highest importance, and therefore this one here, if you search for Nagoya, should be on top. Then, so let's say here this is number 1. The second largest number here is this one, page number 3. And then we have page number 2, page number 4, page number 5. And then at the end you get this page number 1, which should be at the end of the search results. And so this gives you the ranking of the pages, and you can use this to sort your search result. And so it seems that in this case maybe we got lucky. So we had this equation here, and I mean it could be that this matrix A doesn't have an eigenvalue 1, so we cannot find a vector like this which solve our problem. But in this case this always works. So why? So here, so one condition was that the sum of the entries in the columns is 1, meaning one page needs to distribute its importance to the links it sends out. So if it sends out a lot of links, then each of these links just should count by 1 over the number of links. So this just means that the sum of the entries here is always 1. So sum of entries in columns of A. So this is 1. But now we can consider the transpose. So what is the transpose of a matrix? It interchanges columns and rows. And therefore in this case the sum of entries in rows of A transpose is also 1. But what does it mean if I have a matrix where the sum of the entries here is 1? So what happens if I multiply this? So let's say this is A transpose. If I multiply it with the vector 1, 1, 1, 1, 1, 1, 1, then so if I multiply this with this here, and I know the sum of the entries is 1, then this will be exactly the same vector, 1, 1, 1, 1, 1, 1, 1. So therefore, this AT has eigenvalue 1 with the eigenvector 1, 1, 1, 1, 1. But now, what is the connection between the eigenvalues of the transpose of a matrix and the matrix itself, where the eigenvalues of a matrix are the zeros of the characteristic polynomial? But we know that, so what is the characteristic polynomial of, so maybe this is not an implication here, the characteristic polynomial of a matrix is given by the determinant of A minus lambda times the identity matrix. But we know that the determinant of a matrix is the same as the determinant of its transpose. So we could take the transpose here. And the transpose of a sum is the transpose of each summand. So this is the transpose of A. And here the transpose of the identity matrix is just the identity matrix. So this is just this. And therefore this is the characteristic polynomial of the transpose. And now we see in this case that the transpose of A has eigenvalue 1. This means that 1 is the zero of its characteristic polynomial, but because this is the same as the polynomial of the matrix A, 1 also needs to be an eigenvalue of this characteristic polynomial, and therefore eigenvalue of A. So therefore 1 is also an eigenvalue of 1. And in general we see that the eigenvalues of the transpose of a matrix is always the same as the eigenvalue of a matrix A itself. But the eigenvectors are completely different. So we see here that in this case 1, 1, 1, 1, 1 is always the eigenvector for the eigenvalue 1 for the transpose. But in our example here, this is for example the eigenvector for the eigenvalue 1 for the matrix A. But first here the statement is 1 is eigenvalue of A. And therefore we can always solve this problem in this case. So every time we have this linked matrix which has this special style like this, then we can always solve this equation AX equals X, and then we can always find a ranking for pages like this. Okay, so this was the second example, and now the third example is related to decision making, and let me use this input here. So this is part of the so-called analytic hierarchy process. So if you look for AHP, then you will see that what I will describe is one small part of this decision-making process. And the example I will do, as you can already see, is quite stupid again, but this really has application if you, for example, if you're in a company and you need to decide where you spend your money or on which projects people should work. So how do you spend your time? Then there will be a lot of things you need to, so there will be a lot of different projects. So let's say we have 100 projects and you want to say, which project is the most important. So the idea is that we want to find a ranking for a lot of objects, and this is quite difficult if you have a lot of objects. In this example here we will have a small number of objects, and then maybe you don't need this method, but I wanted to keep it simple. So the main idea is, as I said, if you have some objects and you want to order them, similar to the web pages, but now in a different way. And the main idea is that if you have a lot of things, it's quite hard to say this is the best, this is the second best, and this is the third best. But what you want to do here now is just compare them pairwise. So you pick two out and then look at this and look at this, and then it's quite easy to say, well, this is maybe a little bit more important than this. And then you put it back and you take two different, and you can say this is more important than this, and so on. So what we want to do is, so the example I will do here is dinner places in Nagoya. So if I ask you what is the top 5 or the top 4 of your dinner places, then maybe it's hard to say, well, maybe the first place is clear, and then second and third you're not sure. But now what we want to decide is what is the ranking of these 4 places here. So we want to find numbers x1 up to x4, and this we will do by comparing them pairwise, meaning we will have approximations for the fractions of these importance. So this just means that if x1 is more important than x2, then x1 divided by x2 should be a big number. So let's do this in this example here with the Ichidan, 711, Misen, and Akakara. So let's do, well, of course I already did this before, so I just need to copy. So we now want to compare them pairwise and then collect these numbers and then see how this can help us to find a ranking for all of them. So first of all, let's compare Ichidan and 711, where this is, in my case, for me easy, because I'm a big fan of Ichidan. So I say that 711 is for me 4 times better than, that Ichidan is 4 times better than 711. And then I will say, well, Misen is nice, but still Ichidan is twice as good as Misen. And here, Ichidan and Akakara, well, maybe that's 3 to 2, so it's 1.5 times better than Akakara. And so, okay. And now 711 and the Misen, let's say maybe Misen is better than the 711, and here 711 Akakara is 3 times better, and maybe I have a tie here between Misen and Akakara, because I'm a big fan of spicy food, but by a direct comparison I'm not sure which one I should prefer. So what these numbers now give are somehow approximations for so this somehow says that's an approximation for the x1 divided by x2 is given by 4, and here an approximation for x1 divided by x3. So each one was 1, and so this is how was the ordering? 7, so we have 1, 2, 3, 4. 711 was number 2. So this is just the order, not the importance. 3, 4. So here we had the approximation 2, and here this means that we have the approximation for this value to be 3 over 2. So what we do now is we write these comparison into a matrix. So first on the diagonal it's clearly 1. And so again 711 and Ichidan, I said Ichidan I think is 4 times better. But this on the other hand then also automatically gives me this entry. 711 Ichidan is always the inverse. And then we have 2 and 3 over 2. What did I do? 1/2, 1/3. And here in this case, Akakara and Misen, I said, are the same. So here on the other side of the diagonal, it's always the inverse, because it's a comparison in the other direction. And 1/2. Okay, so this is now a matrix which comes from a pairwise comparison objects. And now the claim is, so claim that an eigenvector to this matrix for the dominant eigenvalue gives a good approximation for a ranking of these. So an eigenvector of A to the dominant eigenvalue gives a good approximation for a ranking. So meaning in this case we can maybe we can go back here to Python. So let's go back here to this thing, and yeah, so here I oh sorry, I need to do it again. So here in this example I put in exactly the matrix I wrote down. So you can see the first row is 1, 4, 2, 3/2, and then we use our program here to give eigenvalue and this power iteration. So this is the eigenvector. So in this case the eigenvalue is not important, but here the eigenvector is given by, so what is this? X is 0.75, 0.18, 0.41, 0.48. So you can close this again. And this now means the highest number means the most biggest importance. So in this case here we get that the winner is Ichiran, second place is Akakara, and then Misen, and last place is the pasta from 7-Eleven. And now why does this work? So let's so why does it work? Why does it work? Well, assume that we have a matrix and the entries are really given by these comparison. So the matrix, so let's say for example in the case n equals 3, how does the matrix look like? So here's x1 divided by x1, which is 1, x1 divided by x2, x1 divided by x3, x2 divided by x1, x2, x3, and here x3 divided by x1, x2, x3. So remember, so these are the things we get out of the pairwise comparison, and what we want to find are the actual values for x1, x2, and x3. But what happens here if I multiply with the vector x1, x2, and x3? Well, you see that here if I multiply this, I get x1. If I multiply x2 with this, then the x2 cancels, I get x1. And here if I multiply this, then the x3 cancels. So actually here I have x1 plus x1 plus x1. And also in the second row I get x2 plus x2 plus x2. And in this third I get x3 plus x3 plus x3. So in this case I get 3 times this vector x1, x2, x3. And in general, if I have an n by n matrix like this, then I will get n times the vector x1, x2 up to xn. So this vector here is an eigenvector of this matrix for eigenvalue 3. But also so the eigenvalue of this matrix is well, in general n. But also, what happens if I multiply this matrix with let's say with x1 minus x2 0, then you see that that the first column gets always x, here it's x1, x2, x3, and the second is minus x1, x2, minus x3, so this gives 0. So we see that this vector here is an eigenvector with eigenvalue 0. So we see the second eigenvalue is 0, but also the third, fourth, and so on are eigenvalues 0, because the eigenvectors, so for lambda 1 we saw it's x1 up to xn, this is the one we want, and here this one is x1 minus x2 0 0 0, so this you should check that, for example, if I take minus x3 in the third position here, then this is also an eigenvector with eigenvalue 0 up to this vector here, x1 up to minus xn, and in between is 0. So we see that here again it's another example where we are interested in an eigenvector for the dominant eigenvalue. And of course here in the example these values are just approximations. You see that, for example, it's a little bit inconsistent how I did it here, because here I said Akakara and Meson is the same for me, but here I said that Akakara is actually better than 711 and Meson is not so much better than 711, so here are the different numbers. So it's really just an approximation, and therefore we saw that in Python the eigenvalue was not exactly 4, the eigenvalue was 4 point something. But still, even though if these numbers inside the matrix are not exactly given by these fractions, it still gives a good approximation, the eigenvector. And this gives a good solution to a ranking to these, in this case, restaurants. But of course, in a real-life application, you would have more objects, and then these inconsistencies are not so clear at all. But still, you will get a good solution for a ranking of your objects. Okay, so this is basically all we do for this application part this week. But we will also see how eigenvectors and eigenvalues play a role in electrical circuits. But for this, we'll need to talk about linear differential equations, which we will maybe start next time. And then there we will also see more applications for eigenvalues and eigenvectors. But also you should maybe Google applications for eigenvalues and eigenvectors and see by yourself that there are much more out besides these examples I did today. And then you should also play around maybe with a Python notebook. And yes, then see you next time.